In this lesson, we're going to have a little bit of a detailed discussion about thermodynamics, a subject that puts many a student to sleep. But it's not as bad as you think, and it's actually quite interesting. It really tells us everything we need to know about what reactions happen and which ones don't, whether they give off heat or whether they absorb heat, and things of this sort. And so it kind of gives the underpinnings of why the world works and how the world works. So it's actually a rather interesting discussion here. One thing it can't tell us anything about is the kinetics of a reaction. It will never tell you how fast. It can tell you if a reaction will happen, but it will never tell you how long it's going to take. So just one of the limitations, the main limitation of thermodynamics, is it can't tell you anything about rates and kinetics. Just keep that in mind from the get-go. So we'll start off with a discussion of the three laws of thermodynamics. We'll talk about entropy, what it is, and the factors that affect it. We'll talk about Gibbs free energy at that point and what we use to kind of normally figure out if a reaction is spontaneous or not. We'll talk about its relationship to the enthalpy change delta H and the entropy change delta S. And finally, we'll finish this discussion off with a relationship between delta G and both the reaction quotient and the equilibrium constant. Cool, and if you want to be notified of when I make more of these videos and release them, so be sure to subscribe so that you'll be notified when I do. And if you're looking for practice problems, my Ultimate General Chemistry Prep course on chadsprep.com has got plenty of practice problems for general chemistry. Okay, so let's talk about the three laws of thermodynamics. So the first law you've probably seen in Gen Chem 1. And it's that energy cannot be created or destroyed. So sometimes we'll call this the conservation of energy. And so you probably even gave this a little bit of a mathematical treatment. We said that delta E equals Q plus W. Now delta E is more properly written as delta U, but in Gen Chem, for whatever reason, we like to call it delta E. But that's the change in internal energy of a system here, and in this case it's equal to Q and W, where Q is the transfer of energy through heat and W is the transfer of energy through mechanical work. So, and all it's really saying is that the energy can't change in a system unless it's transferred in or transferred out. It can't just be created magically out of nothing. So that's where this kind of, is another thing, but another expression of the first law. But we talked about this way back in first semester in chapter 5 on the thermochemistry and stuff. So it's not as interesting now, but much more interesting is this second law right here. So second law says, really three ways to state it, but for a spontaneous process, and a spontaneous process is just one that happens. So if you put a block of ice at room temperature, it will melt. But if you have water at room temperature, it will not freeze. So reactions that happen like this, or processes that happen, are spontaneous, and ones that don't are non-spontaneous. So for a spontaneous process, the entropy of the universe increases. Now, this word entropy is a little bit nebulous here, and so we usually oversimplify it for our freshmen and things of this sort. And suffice to say, we say, oh, well, it's disorder. Well, it's not disorder. It correlates with disorder. If disorder goes up, entropy goes up and stuff like this. But properly, it's actually not exactly the same thing as disorder, but they go hand in hand, so to speak. And that's just conceptually easier to understand. It actually has a mathematical definition that we'll get to a little bit later. But for now, I will just go along with the fact that it's related to disorder. And if disorder goes up, then entropy is going to go up as well. And so in this case, for a spontaneous process, the entropy of the universe increases. That's your second law of thermodynamics. So a couple different ways to state that second half of this. So you always want to start off by saying for a spontaneous process. Well, if the entropy change or the entropy of the universe is increasing, we could say that the delta S of the universe is positive. That would be another way to phrase it. So instead of saying that the entropy is going up, well, for anything that's increasing, that means the change is a positive number. So, and then finally, we could say for a spontaneous process, turns out there are two things in the universe. And if you've ever been in love, you know this. There are two things in the universe. There's the person you're in love with, and there's everything else. Well, in chemistry, we take a similar kind of dichotomy. We say that there's the thing you're looking at, that's your system, and there's everything else around it, and that's the surroundings. And so another way to say that the delta S of the universe is positive is to say that the delta S of your system plus the delta S of your surroundings is positive. So the sum of the two. Now, nothing says the delta S of your system can't be negative, but if it is for a spontaneous process, well, then the delta S of the surroundings is going to have to be even more positive than it was negative, if you will. So, and typically when we give you like the delta S of a reaction, we're giving you just the delta S of the system in that case. And delta S of reactions can be negative. Nothing that says they can't, so to speak. But the delta S of the whole universe, system and surroundings combined, that's what has to come out positive for a spontaneous process. So on this exam, this is if you're going to be, tested on one of the laws, the second one is definitely by far the most common one for you to test on. One, it's new, and it's important, and it's complicated a little bit, so definitely the one. Third law of less importance on this exam, and the true ramifications of this third law is something that's probably going to be lost on us in this class, but third law says a perfect crystal at 0 Kelvin, so all the way to absolute zero, complete absence of heat, so is going to have 0 entropy associated with it. And that's just something to kind of file away in your head. But a perfect crystal is one that is perfect in every way. It's got no impurities, is a big important part of this. So, and it's forming a crystal. It's not kind of just randomly hodgepodge. It's actually in this crystalline structure. And so a perfect crystal at 0 Kelvin has 0 entropy. And there is an importance to this that, again, will be lost on us in this class. But suffice it to say, you're just supposed to memorize it and memorize it as the third. So one, you're definitely supposed to know these 3 laws, but you're also supposed to recognize them by the first, second, and third. So if I say second law, you're supposed to know exactly what I'm talking about. For a spontaneous process, the entropy of the universe increases. Cool. These are your 3 laws. Let's move on. So let's talk about entropy here. And we said earlier entropy is correlated with disorder, but it's not exactly the same thing. It actually has a mathematical definition, and there's actually a couple different definitions, and one of them here is this guy here. So S equals K ln W, where here K here, sometimes written with a K little b, is the Boltzmann constant. So, and W here is what's called the number of microstates. And the second here is S equals Q reversible over T. So the amount of heat transferred into or out of a system in a reversible way, divided by the temperature in Kelvin. So both of these are definitions, and they're, again, mathematical definitions of entropy. We'll talk about a little bit about what they mean here. So first thing here is we got this Boltzmann constant here, but then it's natural log of the number of what we call microstates. So W here stands for the number of microstates. And so what in the world is a microstate? And that's a little bit tough to define, but suffice to say, a microstate is just a different way that a system or particle can exist. So it's kind of a little bit of a nebulous definition. So for example, if we talk about number of microstates here and stuff like this, for example, let's say we talk about ideal gases. So ideal gases, so we look at the number of microstates they can have. Well, it turns out they can travel in the x direction, the y direction, and the z direction. So, and there's more entropy associated with each one of those. We call them degrees of freedom. So more microstates possible because you can move in all 3 directions. Now, if you have a gas, let's say, that is diatomic and has bonds, you can also vibrate those bonds. And there's different vibrational energy levels as well. And so that leads to more possible microstates that molecule can exist in. It can exist in a lower vibrational mode or a higher vibrational mode. So, but it leads to more microstates, and more microstates is going to lead to more entropy. So then you can talk about different bonds that can rotate if you get even more complex molecules. And when bonds rotate, all those individual rotations that are possible lead to more possible microstates that those kind of molecules can exist in. And so what you can take from this with microstates is that, the more complex a molecule is, the more microstates it'll have and the more entropy associated with it. Or the more complex a system is, if you have a collection of molecules and stuff like that. And we'll see some other properties for dealing with systems here in just a second. But that's kind of entropy. More microstates, more entropy, and more complexity in either in the type of molecule you have. If it has more atoms, more variety of atoms, things of a sort, it's going to have more microstates and therefore more entropy. Now, you may have to do a little bit of a calculation with this and stuff like this, but you might not. Now, the lowest amount of entropy anything can have is actually 0, and you'll see that'll actually occur when you have exactly 1 microstate. If you as a particle can only exist in one way, and that's it, well, the natural log of 1 is 0, and you'll have 0 entropy. And so, the more different ways you might be able to exist, these more microstates, then the more entropy is associated with that particular particle or system. All right, this one we're not going to use a whole lot here today. I'll pay it lip service a little bit later and stuff like that, but if I say we'll kind of just treat him a little bit later. Okay, so we're going to talk about some factors affecting entropy. So, and your phase of state is the single biggest factor. So if we look at gases versus liquids versus solids, we see that gases have significantly more entropy than either liquids or solids. And if you kind of take a look at this, so solids, and especially crystalline solids, have a very ordered structure. You have atoms, molecules, or ions kind of in a well-defined positions. And they might vibrate a little bit, and the higher the temperature, the more they might vibrate, but they're still in pretty well-defined positions in a crystal structure. And so they're fairly highly ordered. And again, we had this correlation between disorder and entropy. So if we have a high degree of order, that's not a lot of entropy. Now, if you go to liquids, all of a sudden now we don't have a crystal structure. So, and not only do you not have a crystal structure, but now your molecules, atoms, ions, whatever, are free to move to a certain degree. So, and having motion increases the number of microstates, increases the amount of disorder, and increases the amount of entropy. And then finally, you go to gas. So, and in the gas phase here, you now got, again, the ability of atoms, molecules, ions to move around. One, they're more spread out generally, which leads to more microstates. So, and they're moving faster, which also, again, leads to more microstates and more entropy. So one thing I like to kind of, think about the difference between gases and liquids or solids. Well, gases take up way more volume. So my office here is like, I don't know, 12 by 12, 10 by 10. I don't know. It's not very big here where I'm filming this. But if I told you, hey, I hid a 1 kilogram gold bar somewhere in my office, and if you can find it, you can have it. So you probably should take me up on that, and there's not a lot of places for me to really hide it here. And, within an hour, I'm pretty confident you'll find it. But if I said, hey, this 1 kilogram gold bar, I hid it somewhere in Arizona, and that's all I gave you, well, I think you should just give up before you start, unless you know me really well or you had somebody follow me while I was hiding it or something. But otherwise, there's just way too many locations for me to hide it. And so in this case, I like to think of like the number of locations I can hide it as kind of like similar to or analogous to the number of different microstates. And again, with gases taking up way more volume, the atoms and molecules in that system can occupy way greater number of microstates and have way greater entropy and disorder associated with them. So this is the single biggest factor affecting entropy. It's just your phase of state, and gases have the most by far. Liquids have slightly more than solids, but gases have significantly more than either liquids or solids. All right, so we can also relate this to temperature. So if you have a higher temperature, then you're going to have higher entropy as well. So, and the idea is that, as you raise the temperature, you get more molecular motion. And whether that be in the solid phase, where things are just vibrating more and more and more at higher temperatures, or in the liquid phase or gas phase, atoms, molecules, ions are all moving faster as you raise the temperature. And again, the faster they're moving, the more disorder associated with that, the more entropy associated with that as well. So temperature, also a big factor. And if you recall, the third law says, if you cool a perfect crystal all the way down to 0 Kelvin, that's when it'll have 0 entropy. And as you gradually heat it up, it gets more and more and more. All right, next one. So higher volume, higher entropy here. And this in particular, we usually kind of associate with gases. So, but the more volume a gas takes up, so the more microstates it can have, the more disorder it can have, the more entropy it can have as well. And so in this case, if you want to look at, larger volumes, if you have the same sample of gas, but 2 different volumes, well, whichever one's bigger, there you go. So like say I have 1 mole of helium gas. Well, if I have 1 mole of helium gas taking up 22.4 liters versus taking up 44.8 liters, it would have way more entropy when it takes up a volume of 44.8 liters. Now, if it was 1 mole of helium in either case, it'd have the same number of particles. But with that much larger volume, it'd have much larger entropy. Now, you could also relate this to pressure though as well. So again, if it's the same size sample, same number of molecules or moles of gas, so then you could say, well, higher volumes occur with lower pressures. And so you could also relate this to pressure if you wanted to for a gas, assuming you had the same number of particles. Be an easy comparison. So whether you want to say higher volumes, higher entropy, or for a gas, lower pressures, higher entropy, same diff. Cool, which brings us to our last one. And higher number of particles will get a higher entropy as well. And so if I have, 1 mole of an ideal gas at STP versus 2 moles of a gas at STP, with greater number of particles, so I'm just going to have more entropy associated with it and stuff like that. So overall greater number of particles, which again you can relate to greater number of moles like sort of gas and stuff like that. So is it going to be associated with greater entropy as well? So these are kind of our main factors affecting entropy. And now we're going to use these to figure out how do we tell when a process or reaction has an increase or decrease in entropy for that reaction for the system. All right, so if we want to predict the sign for the delta S of a reaction, so we'll take advantage of what we know here, and gases have way more entropy than liquids or solids, and so the single biggest determining factor of whether or not there's going to be an increase in entropy, a positive delta S, or a decrease in entropy, a negative delta S for that reaction, is going to be a change in the number of moles of gas. And so here if we put increase in moles of gas, then delta S of the reaction is definitely going to be positive. So if we take a look at an example here, so let's say I've got solid like carbon, graphite, let's say, so plus O2 gas. Let's balance this properly. So a lot of students see something like this, and they're like, oh, I've got 3 particles going down to 2. And they're like, Chad, you told me that more particles, more entropy. So, but you got to be careful. The single biggest factor, though, is moles of gas. Not total number of moles of particles, solid, liquid, and gas, but moles of gas specifically, since gases have way more entropy than liquids or solids. And so when I look at this, I really should kind of just ignore the solid. They have so much less entropy than the gases that really, when I look at this, it shouldn't be 3 particles going to 2. It should be 1 mole of gas going to 2 moles of gas. And this is going to have a big fat positive value for delta S. Delta S definitely going to be greater than 0 for this reaction. And again, when we say delta S is going to be positive here, we're not talking about the whole universe now, just the reaction, which is just the system here. All right, so that's the first thing we'll look for. So second thing we want to look for here is phase changes. So you guys, again, we've looked at the different entropies associated with all the phases. And so if you look at your different phase changes, so solid to liquid, liquid to gas, solid to gas. And in this case, solid to liquid, you might recall, is called fusion. Liquid to gas is called vaporization or boiling. So, and fusion as well, melting, same diff. So, and then finally, solid to gas is called sublimation. And in every single case, we're going from something with lower entropy towards something with greater entropy associated with it. And so all of these are going to have positive values for delta S. So they're all, it turns out, endothermic, and you learned this last semester in chapter 5. So in being endothermic, they're also going to have positive values of delta H. So that's not new, but we will, take this into account later on. So I want to bring it back up. So, but in this case, delta S and delta H, both positive values for melting, boiling, and sublimation. Now, if we look at the opposite processes here, cool. You got to rememorize these names if you've forgotten them. So liquid to solid is going to be freezing, or sometimes we call it crystallization. So gas to liquid condensation, and then gas to solid, either deposition or vapor deposition. And that's the one we know students often forget, gas straight to solid. So deposit that in your head. It's called deposition. And in this case, these all go from something with more entropy towards a phase with less entropy. And so delta S for every one of these phase changes is going to be negative. So, and also they're the exact reverse processes of these up here. If these were endothermic, then these are going to be exothermic and have negative delta H values as well. Cool, so just something to file away in your head. So again, if you're trying to figure out the sign on delta S of a reaction, so one, look for change in moles of gas first. Second thing though, look at your phase changes, because you know the sign for every phase change possible and stuff like that. So, and finally, your third thing. Cool. And this one's going to be a little bit nebulous, and this is going to be the least common, method you actually need to employ here. But an increase in complexity, so it's going to lead to a positive value for delta S as well. And obviously, then a decrease in complexity would be the opposite, a negative value of delta S. So in this one, you're only going to use it if you can't use the first two here to kind of determine whether you've got an increase or decrease in entropy. So again, moles of gas, the first thing you should use. And if that doesn't help you, if there's no change in moles of gas, then you could say, well, are we doing a phase change? So, and if that doesn't help you, then you might have to look at something something like complexity. So, and if you're going from less complex molecules to more complex molecules, like you're getting, molecules that have greater variety of atoms and more atoms and stuff like this, that might be it. It could just simply be complexity in terms of overall number of particles. If there is no change in overall number of moles of gas, but there is either an increase or decrease in the number of particles, that could be your thing here as well. So complexity is a little bit nebulous in what it might be. It might be the absolute number of particles when there's no change in moles of gas, or it might be the complexity of the molecules themselves from reactants to product side. All right, now we have a little discussion on Gibbs free energy. So, and Gibbs looked at the second law of thermodynamics and said, oh, if I want to figure out if a reaction is going to be spontaneous, I got to measure the delta S of the whole universe. So, and that's system and surroundings. Well, that's a little bit of a pain in the butt. And so he came up with his free energy. So instead of having to measure something for the whole universe, you can just measure delta G of just the system and figure out if a reaction is spontaneous. And he figured out that if delta G comes out negative, then a reaction will be spontaneous. Whereas if delta G comes out positive, then a reaction will be non-spontaneous, or we might say spontaneous in the reverse direction. And then finally, if delta G equals 0, that occurs when a reaction has reached equilibrium. Okay, so what is Gibbs free energy? Well, simply put, it is the energy available to do work. It's the energy that is free to do work. So when you think of free energy, don't think like it's free energy for everyone. So it's not that kind of free. It's like, are you free for lunch on Friday? Are you available for lunch on Friday? It's that kind of free. So it's the energy that is available to do work. And if a system does work, it's going to lower its free energy. And that's why spontaneous reactions always lower the free energy of the system. They use up some of their energy that was available to do work. So, and for a spontaneous process, delta G is negative. For a non-spontaneous process, it's positive, so on and so forth. So if I let go of this marker, what would be spontaneous? For it to fall or for it to rise? So, and it would be spontaneous for it to fall. Without any outside influence, that's what it's going to do. So, however, we could envision a situation where it would rise if I raised it up myself. And so in this case, non-spontaneous processes aren't necessarily processes that don't happen, but they're going to need the input of energy from an outside source, something outside the system, something from the surroundings to actually occur. All right, so it turns out reactions always want to tend towards a minimum in free energy, and once you reach that minimum, so then you're done, so to speak, and you've reached equilibrium. And because you reached equilibrium, you're not going down anymore, you're not going up, you're just staying right there at the minimum in free energy. So, and that's why for a reaction that's reached equilibrium, you now have a delta G equal to 0. It's no longer changing anymore. All right, real important relationship here is the relationship between Gibbs free energy, the change in enthalpy, and the change in entropy of the system, and finally as well as the temperature. So a lot of times we like to say that you need to get higher test scores as a way of remembering this, and whether you need to memorize this or whether it's going to be provided for you is really up to your professor and stuff like that. But if you do need to memorize it, get higher test scores is a great way to do it. Now, in one example, I've written this equation with these little circles up here, and in the next I have not written with those little circles. And my question for you is, what do those little circles mean? And hopefully you said it means standard conditions. And so we can use this equation under standard conditions, or we can use it under non-standard conditions. So we got to talk about what those standard conditions mean, and we don't want to confuse them with STP that we learned when we had a discussion on ideal gases. So STP was standard temperature and pressure, and it defined a temperature and a pressure of the system, and that standard temperature was always 273 Kelvin, 0 degrees Celsius, and the standard pressure was 1 atmosphere. And that's not what we're talking about here at all. Standard conditions is not so concerned with the overall temperature. You can actually have standard conditions at any temperature. I could have standard conditions at 400 Kelvin, standard conditions at 298 Kelvin, standard conditions at 120 Kelvin. So however, I say that kind of tongue-in-cheek because most of the time your Gen Chem textbook will give you a bunch of standard values and tables in the back of your book at 298 Kelvin. And it only provides them only at 298 Kelvin. And so oftentimes we get under the impression that standard conditions actually implies 298 Kelvin. Well, it doesn't. But oftentimes a lot of published data only give you standard values at 298 Kelvin. So keep that distinguished. It doesn't actually include that, but sometimes we just kind of like ignore that and kind of pretend that it does, but it really doesn't. What standard conditions actually means, though, is that you have for any aqueous species a 1 molar concentration, whether it's a reactant or a product, all of them 1 molar concentrations, or if it's a gas, a 1 atmosphere partial pressure. That's what standard conditions deals with. So it doesn't deal with what temperature you're at, it deals with how much of the reactants and products you have. Equal amounts, all equal to 1, whether it be 1 molar if they're aqueous or 1 atmosphere if they're gaseous, but all reactants, all products present in equal amounts at concentrations of 1, so to speak. That's what standard conditions actually refers to. So, and you can have delta G under any kind of conditions, and so it's convenient that they define them at these standard conditions because that's what they'll publish them at. Because outside of that, you can have any concentrations you want, and you have this infinite supply of these non-standard conditions. And so it turns out they decided to call this the standard, 1 molar concentration of all reactants and products, or 1 atmosphere if they're gases. And then they gave us an equation that allows us to relate a non-standard value to those standard values and stuff like this. But that way they can publish them from one major set of conditions, and we can then relate any kind of non-standard conditions to those. But this equation works under standard conditions or under non-standard conditions, and I'll kind of treat it interchangeably. So however, later in this discussion, we'll talk about, delta G standard versus delta G. And we'll treat them very differently, as we'll see. But for now, in this equation, though, we can either do it all under standard conditions or all under non-standard conditions. So turns out delta G depends on 2 major things here, and that's delta H and delta S. So before we actually kind of have this discussion, I got to make sure your math skills are up to par. So little review here. So what do you get when you add a positive number to another positive number? Hopefully you said an even larger positive number. That's the kind of math skills we're going to need here in a minute. What do you get when you add a negative number to another negative number? And if you said a positive number, you were multiplying. I just want you to add them. So a negative number to another negative number, you get an even more negative number. And finally, if you add a positive number to a negative number, it depends on which one had a greater magnitude. That's the level of math we need to do this next discussion here. So we're going to look at delta G equals delta H, and we're going to look at this as plus negative T delta S. So we'll look at a little bit funny here. So we're going to look at delta H, delta S, and we're going to look at the sign on each one of these and what it actually implies. All right, so if we want a reaction to be spontaneous, then we want delta G to come out negative. And if we want delta G to come out negative, well, then delta H itself should be negative. And then this term right here should also be negative. And as long as these 2 terms, not just delta S, but negative T delta S, so delta H and negative T delta S, as long as they're both negative, well, then when I add them together, delta G would have to come out negative. And when's that going to happen? Well, I want delta H for sure to be negative here. But to make this second term come out positive, to make this second term come out negative, then I need delta S all by itself to be positive. So we have a negative sign out front, and then we have temperature. And keep in mind, temperature here is in Kelvin, which means the lowest you can go on the Kelvin scale is absolute 0. You can never have a negative temperature in the Kelvin scale. And so if delta S is positive, by the time you multiply by that negative sign right there, that's when this term will come out negative. And so when delta H is negative and delta S is positive, then this reaction can't help but come out spontaneous. And in this case, what we actually say is that we say it's spontaneous. That's not going to be a good red marker. Let's go blue instead. Spontaneous at all temperatures is how we word this. And you're like, well, where do we talk about temperature here, Chad? Where's this coming from? Well, it's coming from, it's in the equation here. And the idea is that this second term here, negative T delta S, at low temperatures, it's going to have a small magnitude because you're multiplying by a small value of T. But at large temperatures, high temperatures, it's going to have a very large magnitude instead. And so the idea is that, depending on how big the magnitude is, maybe that affects things. Well, it's not going to affect anything in this example because whether I plug in a small value of T or a large value of T, I'm going to get a small negative number or a big negative number, and I'm just going to be adding it to another negative number if we're considering a negative delta H. And if you add 2 negative numbers, I don't care if the second one's a big negative or a small negative, you add 2 negative numbers, you're going to get a negative value for delta G, no matter what T value plugged in. And that's why we say spontaneous at all temperatures. Now, another way to think about this is you want to give the universe what the universe wants. So, and what does the universe want? Well, the universe wants the same thing a girl wants. They want a stable guy. So in the universe's perspective, stable means low in energy. And so to get lower in energy, you have to give off energy. And that's what an exothermic reaction does when delta H is negative. It gives off energy. So, and becomes more stable, we say. So in this case, the universe wants exothermic reactions. Okay, great. So the universe also wants, so according to the second law of thermodynamics, for all spontaneous processes, the entropy of the universe is going to increase. Well, again, this is not the entire universe, this is just the system, but that's a good way, a good step along the way to getting more entropy in the whole universe. And so the universe wants to have more entropy as well. And so in this case, those are the two things the universe wants. If you give the universe both things it wants lower enthalpy and higher disorder, higher entropy, then the reaction can't help but be spontaneous no matter what temperature you run it at. Now, if you do the exact opposite here, so if we have a endothermic reaction, so that results in a decrease in the entropy of the system, well, then you're not giving the universe anything that it wants at all. And so in this case, now we're saying that delta H is going to be positive. Now we're saying that delta S is going to be negative, and a negative times a negative is a positive. And if you add two positive numbers, then delta G is going to come out positive. And again, I don't care if this second number is a large positive value or a small positive value, depending on if you carry it out at a high temperature or low temperature, you're just still adding two positive numbers. And no matter what you do, the reaction is going to come out non-spontaneous. Delta G is going to be positive. And so that's what we'd say here. Instead of saying spontaneous at all temperatures, we'd say non-spontaneous at all temperatures. Another way we could word this, if it's non-spontaneous at all temperatures, we could say that actually implies that it's the reverse reaction that is spontaneous at all temperatures instead. So you should be prepared to see that either way, by the way. That's a little bit tricky way they could word that. So again, if a reaction is non-spontaneous at all temperatures, it means the reverse reaction is spontaneous at all temperatures. All right, so if you give the universe both of what it wants, the reaction will always be spontaneous. And if you don't give the universe either of what it wants, then it'll never be spontaneous. But for a reaction to be spontaneous, you have to give at least one of the things that it wants to even have a chance of being spontaneous. And so we're going to take a look at giving the universe one of the two things it wants at a time. And so when delta H and delta S are both positive or both negative, we're going to find out there's a temperature dependence associated with spontaneity, because you're only giving the universe one of the two things at once. So let's kind of take a look at this one more time. So in the first example, delta H is positive. That's not what the universe likes. So, but delta S is also positive, and that is what the universe likes. So, but if delta S is positive, by again, the time you multiply that negative sign, then the second term comes out negative. And the idea is now that you have a positive term and a negative term, and when you add them together, well, it could come out positive if delta H is a bigger term. So, or it come out negative if negative T delta S has greater magnitude. And the question is, well, how do you know which one's bigger magnitude? Well, you don't. However, what we do know is that this is the term that has temperature in it. And as you get higher and higher temperatures, this number is going to get to be a larger and larger negative number, a negative number of greater magnitude. And so at some threshold temperature, it's going to be high enough that the negative term will exactly equal the positive term, and delta G will come out bigger. I'm sorry, delta G will come out 0. So, but once you cross higher, get bigger than that temperature, so all of a sudden now the negative term is going to win. And so there is some threshold temperature above which the reaction will be spontaneous. Delta G will come out negative. And so the way we phrase that is we often say that this reaction is spontaneous at high temperatures. Cool. And when you think of high temperatures, it's not about you, just so you know. The universe doesn't revolve around us, right? So it's not about what we think is a high temperature. So right now I've got crazy lights all over the place, and it's a rather high temperature. It's starting to get a little bit uncomfortable. It's about 80 degrees in my office right now. So that's 80 Fahrenheit. So, and I consider that a rather high temperature. So, however, if I'm cooking burgers, that would be considered rather low temperature. So everything's kind of relative. And so what a high temperature is here is anything over that minimum threshold temperature. So like if I wanted to melt ice, a high temperature would be anything over 0 degrees Celsius. But if I want to boil water, it would be anything over 100 degrees Celsius. And if I want to melt like sodium chloride, well, then it'd be anything over like 800 and some odd degrees Celsius. So everything is relative. So don't think about high temperatures here and low temperatures in a sec as being anything related to what you think is high and low. It's all relative to just some threshold temperature unique to whatever reaction or process you're talking about. All right, finally, when delta H and delta S are both negative. So in this case, you are giving the universe what it wants in terms of delta H. But you are not giving the universe what it wants in terms of delta S. And so when you give the universe one of the two things it wants, then you get a temperature dependence yet again. And if delta S is negative, then negative T delta S is positive. And if you want delta G to come out negative now, then you want that first term to have the greater magnitude. And so the second term is the one with temperature in it. To make sure it has the smaller magnitude, then you better make sure you do this with a small value for T at low temperatures. And so when delta H and delta S are both negative, we say that the reaction is spontaneous at low temperatures. And again, low here doesn't refer to anything related to how we feel as a low temperature or anything like that. It's whatever process you're talking about. So if we're trying to freeze water, a low temperature would be anything below 0 degrees Celsius. So if you want steam to condense to liquid water, a low temperature would be anything below 100 degrees Celsius. So, and if you notice, I'm picking examples that actually follow this pattern. So we talked in the first example with delta H and delta S positive about either melting ice. And if you recall, we said melting has both a positive delta H and a positive delta S. Or we talked about boiling water. And again, going from liquid to gas, also positive delta H and positive delta S. And now with both negative, that's why I'm talking about freezing. So going from liquid to solid has both a negative delta H and a negative delta S. So you can also then remember these temperature dependencies. If instead you don't want to work out the math like this, you could think about what phase changes you know. And you could think, well, let's talk about freezing for a minute. Well, freezing is negative delta H and delta S, and it only happens when you're below a certain threshold temperatures, i.e. they're spontaneous at low temperatures. Talk about boiling water. Well, for boiling water, delta H and delta S are both positive. And you can only boil water if you're above 100 degrees Celsius, i.e. spontaneous at high temps. So if you remember your phase changes, that might help you memorize this as well. Now, at the end of the day, we just kind of derive this chart. You have to know all 4 of these conditions. Whether you just memorize this chart, about half my students generally do that. So whether you can work out the math, about half my students do that. So take your pick though, but at the end of the day, you have to know kind of when a reaction is going to be spontaneous under each of these 4 sets of conditions. At this point would be now when I normally would say questions to my students. So if you got questions, I guess put them in the feed down there on YouTube. All right, so here I'm giving you a reaction, and the question really is just, is this reaction spontaneous at all temps, no temps, or high temps or low temps? So when is this reaction going to be spontaneous? And if you look, I gave you that delta H is negative. That's just given. Okay, so we know it's exothermic. And if we know it's exothermic, we know it fits into one of 2 places. It either is going to be spontaneous at all temps, or it's going to be spontaneous at low temps. But to figure out which one it is, we got to know if delta S is positive or delta S is negative. And it wasn't given. However, we learned a little bit ago how to predict the sign of delta S. And in this case, the most important thing was always change in moles of gas. And we're going from 2 moles of gas to 1 mole of gas. A decrease in moles of gas is associated with a decrease in entropy. And so in this case, we don't have a numerical value, but we do know that delta S is going to be negative. And because delta H and delta S are both negative, we now know that this reaction would be spontaneous at low temps. How low? I don't know. So, but some threshold temperature is how low it would be. And again, if you want to figure out how low that would be, well, that was going to occur when delta H, the absolute value of delta H would equal the absolute value of negative T delta S. And so if you had delta H and delta S actual numerical values, you could solve for what temperature would be that threshold temperature below which this particular reaction would be spontaneous. Now, one thing to note, if you are doing calculations with either this equation Or with this one, and then you might be just straight up doing some plugging and chugging here. Notice you got 3 variables and a temperature here. I give you 3 out of those 4 variables. You solve for the 4th one. Well, you might be doing some plugging and chugging. Be careful on your units. So delta G and delta H are much larger than delta S for most reactions, and they're usually given in kilojoules, whereas delta S is usually only given in joules. So notice if I asked you, hey, how tall are you? And depending on where you're from, you might be like, hey, Chad, I'm 6'2", or you might be like, hey, Chad, I'm so many centimeters, or something like this. So, but if I rephrase my question, I say, no. How many miles tall are you? Well, I mean, I guess we could figure that out, but nobody would ever ask me how many miles tall I am. It's just not it's a very inconvenient unit. So same thing here with delta S. With delta S being really small, if we express delta S in kilojoules, we're always going to, for a lot of reactions, get something less than 1, and that's not very convenient. In the same way that I'm some small fraction of a mile tall. So, and that's why delta S are usually given in joules per mole, whereas delta G's and delta H's in kilojoules per mole. But when you plug them into this equation, you need to make them all joules or all kilojoules to make the units work. So just be careful. Same thing if you were solving it just like so. All right, now we've got to talk about 3 ways we might calculate either delta G, delta H, or delta S reaction from some published data, like in the back of your textbook or something like this. And it turns out it comes out to a simple equation here. So I want to look at the delta S version first. So for delta S, they actually publish absolute entropies for reactants and products. So, we might do this for me, like, let's say that before I go to a casino, I've got $1,000. And let's just say I'm horrible at poker or whatever, or slots, I just have bad luck or whatever. Just know that I'm horrible. And so I go into the casino with $1,000. I come out of the casino with $200. And if we said, what's the change in money for me? Well, it would be negative $800. I lost $800. So, and all you'd have to know is just, well, how much did you go in with and how much did you go out with? Same thing with entropy. We call these absolute entropies. We can calculate exactly how much entropy any species has. And so if we just compare the amount of entropy that are in the products versus the reactants. So, and just like with the case of me into the casino, out of the casino, if I take how much I left the casino with and subtract how much I went in with, so 200 minus 1,000, I get negative 800. Same thing here. If we take the amount of entropy that's in the products and subtract out the amount of entropy that was in the reactants, we just get the delta S for that entire reaction or process. So keep in mind, you got to multiply by how many moles you have and stuff like this. So, but it is really just that simple. Same as kind of me in the casino analogy here and stuff like that. So it turns out there's a couple of similar equations for both delta G and delta H, but delta G and delta H are a little bit of a pain in the butt. So we don't actually have absolute values for either delta G or delta H, and so we have to cheat. And to cheat, we use these formation reactions. And you guys used formation reactions probably back in the thermochemistry chapter in chapter 5 for delta H, but also it turns out we're going to use them for delta G as well. And the big deal is this, is that we actually never know how much H or G a species has. So we can do that for S. We know exactly how much entropy something has because we have a reference point. And that reference point was that 3rd law of thermodynamics that says for a perfect crystal at 0 Kelvin, it has 0 entropy. So, but for G and H, we don't have that. So take, for example, let's say I told you I went on a diet and I went on the Atkins diet and I lost 100 pounds. And then I got off the Atkins diet and I gained 50 pounds. So, and then I went on the South Beach diet and I lost 200 pounds. And then I got off the South Beach diet and I gained 150 back. And the question I would ask you is then, well, how much do I weigh now then? And your answer would be, you don't know, because you don't know what I started weighing or what I weighed anywhere along the point. You don't have a reference point. You can calculate changes in how much my weight's changed, after both diets and stuff like that, but you still don't know how much I actually weigh. We have the same problem with both Gibbs free energy and enthalpy is we never actually have a reference point like we do for entropy. And so we cheat. They created these formation reactions that they can measure the delta G for or the delta H for, and they create them in such a way that if you just simply do products minus reactants in the same way, you'll calculate either delta G or delta H of the reaction. And so now we have a simple plug and chug way to calculate either delta G, delta H, or delta S of a reaction just from tables of data, often provided in the back of your textbook. So we're going to calculate delta H of this reaction. I picked one of the 3. It could have been any of the 3. So, and here I'm going to provide you with delta H's of formation for every species in this reaction, except for one. I didn't tell you what the delta H of formation for chlorine was, for Cl2 gas here was, because I didn't have to. If we added a value in for Cl2 gas onto this table, for instance, we'd find out it would be 0. So it turns out for a formation reaction is the enthalpy or free energy change associated with forming exactly 1 mole of whatever you're talking about from its individual elements in their standard states. Well, if you actually have an individual element in its standard state, for chlorine it is diatomic and a gas in the standard state, well then to go from being in your standard state to being still in your standard state shouldn't have any change associated with it all. And that's why for a formation reaction, so for any element in its standard state, it's going to be a value of 0, and we don't feel the need to have to give it to you in a table at all because you're supposed to know it's 0. Now, don't get confused on this, though. That's only for formation reactions. And again, with delta S, we don't use formation reactions. We use absolute entropies. And this for Cl2 would not be a 0. So the only time you could get down to an entropy of 0, keep in mind, is then if you have a perfect crystal at 0 Kelvin, according to that third law of thermodynamics. But otherwise, you're going to have a value there. But for delta H as a formation, delta G as a formation, that's when an individual element in its standard state would have a value of 0. All right, and so in this case, we're just going to plug and chug here with this middle equation here. So it's products minus reactants. So we got 3 moles of Cl2, which we said was going to be 0. So here we're going to get delta H of the reaction is going to equal 3 times 0. So I'm just pointing that out because you do have to multiply by the number of moles. That's what the N and the M here refer to. So plus the value for pH3, the 5.4, and that's all the products added together, and then we'll subtract out all the reactants. And so in this case, we've got PCl3's value, which is negative 288.07. So combined with 3 times HCl's value, so 3 times negative 92.3. Cool, and don't forget you're subtracting all of this that's in the brackets here. And so if you work this out, and I punched this into my calculator already, and if you don't want me to ruin this for you just yet, just hit pause. So, but otherwise, I'm just going to give you the answer here. Delta H, it's going to come out to 570.37 kilojoules. Okay, so now we know how to very quickly get delta G, delta H, and delta S from tabulated data. Now, if they're going to, ask you a really super kind of involved question on an exam, what they might do is give you enough data to calculate 2 of these 3, either delta G and delta H and delta S, or delta G and delta S. They'll give you all the data, reactants and products, to calculate 2 of the 3. And that way, once you go and calculate those 2, then they'll say, well, then what would the other one be at a certain temperature? And you'd have to go back to using get higher test scores equation here. So to get the third one. So if I gave you all the tabulated data here, not just for delta H, but also for delta S, so you calculate both of them, and then I said, what would delta G be at, say, 298 Kelvin? Well, then you'd plug in the values that you tabulated up, products minus reactants, for delta H and delta S, plug in the temperature, and now you could solve for delta G as well. It would be a very involved question, but I have seen it show up quite regularly on general chemistry exams for this chapter. Okay. So one thing we need to point out here is a little more about what these formation reactions are. So again, keep in mind, you didn't have to know what a formation reaction was to use it. We just used it. We did products minus reactants, boom. We didn't even talk about what, too specifically what a formation reaction actually is. But if I give you all these formation data, just like we did here, you're just like products minus reactants, done. Cool, and this is, a lot of things like this, right? You eat every day without probably knowing how everything works. I doubt, you probably ate breakfast this morning, and I doubt you shoved food in your mouth and sat there and thought, right now my salivary amylase is breaking down some starches, breaking those glycosidic linkages, and and then you swallowed, and you're like, yep, now the muscles lining my esophagus are doing peristalsis, pushing it down, and now it's going to pass through my cardiac sphincter and into my, you didn't think about any of this stuff. You just food pie hole, and you shoved it in, and you ate, and you didn't even have to know how all your digestive system works. Cool, same thing here. We didn't have to know what a formation reaction was to be able to use it. Products minus reactants, done. However, you do have to know what a formation reaction is as kind of a standalone question. So in a formation reaction forms exactly 1 mole of anything you want to talk about. And the one I want to focus on here is we'll do this one for HCl for a minute and talk about, well, where did that 92.3 value came from? Well, it turns out that was the delta H for reaction that formed exactly 1 mole of HCl gas. And what did it form it from? From individual elements in their standard states. So a formation reaction has two parts. The product side is 1 mole of one thing, one product. The reactant side, though, is going to be the elements that make up that product. So in this case, that's elements of hydrogen and chlorine. And they have to be in their standard states, which means if it's diatomic, those 7 diatomics, never have fear of ice cold beer, you got to know those. And it turns out hydrogen and chlorine are both diatomic. And you got to know who the solids, the liquids, and the gases are. And most of you have access to a periodic table that shows all the black ones on the table are the solids that, under standard conditions. The red ones are gases, and the couple of blue ones, bromine and mercury, are liquids. So, but if you don't, then maybe you got to memorize a little bit here. So, but these are both gases under standard conditions. So, and then you got to balance it. So, and in this case, you want to keep this as forming just 1 mole. Normally in Gen Chem, we might put, a 1 here, and make that a 2. But the moment I make that 2 moles of a product, that's not a formation reaction anymore. And so if there's fractions, you just got to deal with fractions. And if you don't like fractions, well, then use decimals and use 0.5 and 0.5. But you're stuck here. You can't double through, or that's no longer a formation reaction. But it is this equation right here that has a delta H of negative 92.3 kilojoules. That's where this number comes from. And it turns out people design these in just such a way that if you do products minus reactants, it just allows you to calculate delta G or delta H for an entire reaction. It's a beautiful thing. Cool, so you might get a question that says, which of the following is a formation reaction? And usually the first thing I do is I look on the product side. And any reaction that forms more than one product or more than 1 mole of a product is out. That's not a formation reaction. And once I've eliminated some choices, then I go look at the reactant side and I say the only thing I'm allowed to have on the reactant side are elements, no compounds. So in any that have compounds, I cross those out. And then finally identify those elements that are in their standard states. So, and usually it comes down to like solid, liquid, gas. But in the case of carbon, you might want to know that it's not just solid carbon. That's often not enough. Sometimes a professor will get more specific and make you realize that it's solid graphite, not solid diamond in the case of carbon. So let's say we want to get a formation reaction, say for sodium bicarbonate. Another question might just be, instead of like choosing which of the following 5 is a formation reaction, it might just say which of the following is the formation reaction for sodium bicarbonate. So in this case, if it's the formation reaction for sodium bicarbonate, we have to form exactly 1 mole of sodium bicarbonate. And we have to form it from the individual elements that make it up: sodium, hydrogen, carbon, and oxygen. And then these elements have to be in their standard states. Well, for sodium, he's a metal, and all the metals are solids except for mercury, which is a liquid. So, and then hydrogen and oxygen are diatomic and gases. And then finally, carbon, like we said, it's not just solid, it's a solid and graphite. Cool. And then we'll put our plus signs in, and then we got to balance this thing. In this case, 1 sodium, life is good. And again, fraction here, we're stuck. Because I only need 1 hydrogen on the product side, so I need 1/2 of an H2. So 1 carbon, and again for oxygen, I need 3 oxygen atoms. These come 2 by 2, so I'll need 1.5 or 3/2 O2s. That way I get the 3 oxygens. And this now is the formation reaction for sodium bicarbonate. And again, did we have to know this to do the plug-in and chug-in we did a little bit ago? Not at all. So, but if we teach you this, so professors feel the need now, we can actually quiz you about what a formation reaction is, since we had to explain it to figure out why this works and stuff. So just another sort of variant of a question you might see on this exam. One thing to note. So if I asked you this question in Swahili instead of English, if I said, which of the following is a formation reaction, would that be a fair question? Well, if you are in a country where the main language is Swahili, well then yes. So if you're in any other country, well then no. So, and here's the deal. They're not going to ask you this question, in some crazy language that you don't speak or anything, but they might ask it in very technical jargon. And the way they might ask it is they might say, for which of the following reactions does delta H of the reaction equal delta H of formation? And that's a tricky way to say this, but for delta H of a reaction to equal delta H of formation, the only way that's possible is if the reaction you're looking at is a formation reaction. And this is nothing more than just saying which of the following is a formation reaction. So again, for which of the following reactions does delta H of reaction equal delta H of formation? That's no different than just saying which of these is a formation reaction. But it's a lot trickier way to say it, so be careful. That tends to show up a time or two here and there. All right, we're going to close this chapter off with a discussion of how Gibbs free energy relates both to the reaction quotient as well as the equilibrium constant. And so keep in mind that we said that thermodynamics can pretty much tell you everything about a reaction except how fast. So it can't tell you anything about the kinetics, but it can tell you, again, if it's spontaneous or not, if it's giving off heat or absorbing heat, if it increased entropy or decreased entropy. So, and it can also, turns out equilibrium constants are going to come from Gibbs free energy. And so thermodynamics can tell you everything about an equilibrium, whether or not a reaction's at equilibrium, whether it needs to proceed to the right to get to equilibrium, proceed to the left to get to equilibrium. So all those sorts of things, and the equilibrium constant values, whether it favors the reactants or the products, those all come from thermodynamics. So again, thermodynamics can tell you everything about a reaction except how fast. All right, so if we take a look here, turns out, again, we talked about standard conditions, and standard conditions were 1 molar concentrations of all aqueous species, reactants and products alike, and 1 atmosphere partial pressures of all gaseous species, reactants and products alike. And so under standard conditions, you have equal amounts of reactants and products. And so what are the odds that you ever begin a reaction, one, with both reactants and products, and with their concentrations being exactly 1 in both cases? Well, I mean, pretty nil. So not the likeliest of scenarios, but even if you did by chance start under those conditions, well, as soon as the reaction starts happening, as soon as reactants start turning into products, well, then you're no longer under those conditions anymore. And so standard conditions are not super common, but there's an equation that relates what the delta G is going to be under non-standard conditions. And what you do is you first look up the standard conditions value from tables of data, like the whole products minus reactants thing. You get the delta G standard from a book somewhere. And what you can do there is then, well, what if my conditions aren't exactly standard conditions? Well, then start with the standard value and add in this fudge factor. Are you at some other temperature? Great, you're going to get a chance to put that in. And if you don't have a reaction quotient of 1, because again, if all your reactants and all your products are at a concentration of 1, then your reaction quotient, products over reactants, well, 1 over 1, even if you're squaring some things, is still 1. So if you have a reaction quotient of anything other than 1 because you're not under standard conditions, well, you get a chance to put that in right here. And so your non-standard delta G equals your standard plus this fudge factor. And what's nice is well, if you are under standard conditions, well, then Q is 1 and the natural log of 1 is 0. And then your delta G is just equal to the standard value at that point. So that's kind of the basis for this equation right here. Cool. Now keep in mind that it's delta G standard that you get from a book. It is what it is. Whether you're under standard conditions is another story, but the standard value is what it is. But as a reaction occurs, as you're trying to approach a minimum free energy, it is this non-standard value that is continually changing. This value, again, it is what it is. You looked it up in a book. You shouldn't think that, well, I looked it up in a book, but now that I'm doing the reaction, maybe I should look it up in the book again to see if it changed in the book. No, it is what it is. It's this value that's approaching 0 as the reaction is approaching equilibrium. The standard value is what it is. So you might get a question that says, which of the following, is true about a reaction equilibrium? And they're going to say delta G standard equals 0. So, and for maybe some really rare cases that might be true, but for most reactions, that's definitely not true. But if they just say delta G non-standard here with no circle there, so equals 0, that's true for any system at equilibrium. So be careful about that. All right, so if we kind of take a look here, so I'm going to look at a reaction A going to B. So this is pure reactant, so I guess pure A. This is pure product, so pure B over here. And we're going to plot free energy over here. And this is going to be a reaction that is spontaneous under standard conditions. And the reason it's going to be spontaneous under standard conditions is that A is higher in free energy than B. And so in this case, we could kind of map out here, if we kind of just drew this across, this value right here from A to B, that's what we'd call delta G standard. So from just pure A to pure B, that's delta G standard. Well, it turns out if we start out with pure A and we run this reaction, what we're going to find out, so, and I'll take and delete this, as if I'm using a computer, I'll erase the blue here. So I'll run this reaction, we'll see how it goes. And as we start the reaction, we'll start producing some B, and we'll start to have a lowering in free energy. Cool. So, and that's typically what our curve is going to look like. And it doesn't take a straight line. And that's kind of a funny thing. You're like, well, why doesn't it take a straight line here? So, and it turns out it doesn't take a straight line because of a lowering of free energy due to mixing. Here you had pure A, and over here you have pure B, but anywhere in between you have a mixture of both A and B. So in your common experience, like if you put salt in water, or if you mix, say, nitrogen gas and oxygen gas, is that they mix spontaneously. And if they mix spontaneously, then mixing must have a lowering of free energy. And so having a mixture is a lowering of the free energy relative to that straight line if there wasn't any spontaneity associated with mixing, any lowering of free energy associated with mixing. So you might say that, anytime you connect the straight line curve to the actual, I should say the straight line to the curve, anywhere along, here, anywhere, that would be associated with the delta G of mixing. So, and that's again why the actual curve is below the straight line. And so as a result, the minimum in free energy is not just pure B, even though pure B is lower in energy than pure A. It turns out there's going to be some ratio of B to A, if you will, that's got a minimum in free energy, and that's this point right here, and that is the point where we'd be at equilibrium. So that is the point where delta G would equal 0. So if you notice, anywhere before that point, if we start anywhere up here, we're trying to go forward to get to equilibrium, and we have a negative delta G. So, but once you reach right there, you just stay there, you're done. And you're just going to sit there. And as long as you're just sitting there, then your free energy is no longer changing and delta G is 0. Cool. But anywhere before that point, you're going to have a negative delta G value. You might also say that your Q is going to be less than your K value. We learned that a reaction shifts to the right back in the equilibrium chapter when Q is less than K. And in this case, Q is less than K everywhere before you reach equilibrium here. So, and when Q is less than K, when our Q value is smaller than the equilibrium constant value, it turns out your delta G will come out to be a negative number. Now, on the other hand, if you go to the other side here, now you'll have delta G being greater than 0 and Q being greater than K anywhere beyond that equilibrium point. So anywhere over here to get a minimum of free energy, the reaction doesn't proceed in the forward direction. It's actually going to proceed in the backwards direction instead. And so delta G would actually be positive. It would be the reverse reaction that would be spontaneous. The reverse reaction would have a negative delta G, but the forward reaction would have a positive delta G, and Q is greater than K anywhere along those points. And so finally, though, once you get from either side, you're going to approach that equilibrium, and once you finally get there, your delta G is 0, and your Q is now going to equal K. Cool, and that's kind of everything about these, kind of a graph here of Gibbs free energy plotted kind of as the reaction progresses here that you might need to know. All right, so let's say we do reach equilibrium. Let's talk about how this equation changes, because we've got to derive one other equation. Now, you might do some plug-in and chug-in with this equation, and one thing I will tell you to be careful of is R here is often given to you as 8.314 joules per mole Kelvin. So, and keep in mind the joules is the important part here, whereas delta G's are often expressed in kilojoules. And so if you're going to be doing any kind of calculation with this equation, check your units. So if you're trying to calculate delta G here, well then delta G standard here in R either better both be in joules or both in kilojoules, convert one or the other. So be careful with that. So just want to make sure you're aware of that. And this is really important throughout the entire chapter here. So just check your units. Super important. We'll see it's important again in the next equation. Now, if we have a reaction that's reached equilibrium, well then this delta G value here is going to go to 0. The standard value is still whatever it was in the book that we looked it up in. So, but Q, once you reach equilibrium, equals your equilibrium constant, K. That's when Q equals K. And so we can kind of rewrite this equation now. So this is 0 over here. So we've got 0 equals delta G standard plus RT ln of your equilibrium constant. And if we rearrange things just a little bit, we can say that delta G standard equals negative RT ln K. And we've now related the standard delta G to the equilibrium constant. Cool, notice it's not the non-standard value that's related to the equilibrium constant, it's the standard value that actually relates to the equilibrium constant. So, and this kind of makes sense if you think about it for a second. So if you guys recall, so you guys learned that when K was much bigger than 1, then we say that this reaction favors products. So when you reach equilibrium, if your equilibrium constant is way bigger than 1, i.e. products over reactants, well then obviously you have way more products. Okay, great. But we can also relate that back to delta G standard. It turns out if delta G standard is negative, well, if delta G standard is negative, that'll happen when K is greater than 1. And if you look at this, when K is greater than 1, the natural log of 1 is 0, but the natural log of a number bigger than 1 is a positive number. And a positive number times a positive temperature times a positive constant, but times a negative sign makes delta G standard come out negative. So we can look at that mathematically, or we can kind of just look at it conceptually for a second here as well. So if you're under standard conditions again, it means you have 1 molar concentration of all aqueous species, reactants, and products alike. And so you have equal amounts of reactants and products. And if the reaction is spontaneous under those conditions, because delta G standard is negative, well, then the reaction is going to proceed to convert reactants into products. It's going to shift to the right to get to equilibrium. And so we're going to start using up our reactants and creating more products. And at some point, you'll eventually reach equilibrium and you'll have more products than you will reactants. Your K, your ratio of products to reactants, will be bigger than 1, and we'd say that reaction favors the products. So if you have a negative delta G standard, well, if you're spontaneous under standard conditions, well, that's a reaction that has to end up with more products and have a K that's bigger than 1. And we can say the exact opposite as well here. So we could say that if delta G standard is positive, well, that's a reaction that's not spontaneous under standard conditions. It's the reverse reaction that's spontaneous under standard conditions. And again, under standard conditions, you have equal amounts of reactants and products, but this one's now going to go backwards, and you're going to end up with more reactants than products. And so your K is now going to be less than 1, and we'd say that this reaction favors the reactants. There are going to be more reactants present at equilibrium. Cool. And so you learned, back in the equilibrium chapter that depending on if K was bigger or smaller than 1, you'd know if the reactants or products are favored at equilibrium. Now from delta G standard, you can learn exactly the same information. So, and again, you might be doing some plugging and chugging with this equation as well. You might be, given the K value and asked to solve for delta G standard. Great, life is good, and it's just plug and chug. Keep in mind units, again, R, 8.314 joules per mole Kelvin. So if you use 8.314 joules, delta G standard comes out in joules. If you change it to 0.008314 kilojoules per mole Kelvin, well then delta G standard comes out in kilojoules. If they want to ask this harder though, they'll give you delta G standard instead and have you solve for K. And if you rearrange this thing here, you can see that your equilibrium constant is going to equal, to get rid of that natural log, it's e to the power of. So in this case, it would be e to the negative delta G standard over RT. And that's the way this works out. And students often struggle with this. One, because often we're not going to give you this version of the equation, but we're just rearranging this to solve for K. And solving for something under a natural log is a pain in the butt. To get rid of that natural log is the inverse function, the exponential function. The other thing you got to be careful of here is, again, you've got delta G standard right here and R right here. And their units once again have to match so that they cancel either both joules or both kilojoules when you're doing the calculation. So, but last but not least, the biggest mistake students often make is they forget that negative sign when they're actually doing the calculation. Cool. So whether I give you K and have you solve for delta G standard, or whether I give you delta G standard and have you solve for K, you should be prepared to do both. Cool. And that kind of completes our discussion of thermodynamics. And if you're looking for practice problems on any of this stuff, so I've got plenty on chadsprep.com. Wish you guys all the best on your upcoming exam.